So the last topic when it comes to fluids is, now that we've seen stationary, meaning that again the fluid was not moving relative to some sort of container, we now have to start looking at the opposite case, which is when it starts moving relative to the container, which is now dynamical fluids, and start looking at fluid flow. Now, first off, some things to talk about, so we need to come up with some terminology and things like this. So, first things first is, let's talk about viscosity. So let's say we're going to be looking at is, let's say we have a tube. So here's our tube, which then has a fluid moving through it, right? Now, if we thought about more of a realistic situation where our tube has a viscosity to it, basically meaning that what happens is, as the fluid starts moving through the tube, what happens then is you basically start getting a kinetic friction term between the walls of the tube and the fluid, which basically means that if you think about the fluid, so if you think about how the fluid is moving, so every particular location, if you think about more of its velocity, so we think about this as a velocity field. So in this case, if I was looking at some point here in the center, this is going to have the largest amount of velocity since it's not being impeded by any portion of the wall. Now, towards the top, what will happen then is that this might have zero or at least very minimum velocity. And then as I start moving away, the velocity should start getting bigger and bigger and bigger until eventually, again, as I start coming towards the center, this is when I start equaling out to the maximum amount of velocity, and then it should look something similar on this side. Right, so I should have something kind of like this, again, with zero or maybe some sort of small non-zero velocity at this point. So, first of all, these lines that I'm drawing here, these are what are known as streamlines. So these streamlines basically dictate the direction at which the fluid is flowing at a particular location. So these are generally in the direction of the velocity, unless there's an obstruction, but I'll show you what happens in an obstruction. And then in that case, the velocity is actually tangential to the streamlines. But this is typically what we would think of for a realistic type of fluid. So again, near the walls, there's going to be some sort of viscosity term, which is basically the same thing as a kinetic friction. So there's going to be kinetic friction across here, which is going to basically slow the flow of the fluid near the walls. But then again, as I start moving away, this thing is going to expand out and then reach its maximum velocity towards the center. Now, we're going to ignore viscosity. So basically meaning that if you ignore viscosity, so in this case, if you had your tube, so let's redraw our tube. When you ignore viscosity, what's going to happen in this case then is that all these velocity vectors will be exactly the same length. So no matter where it is that I'm looking at in the tube, all of the velocity vectors that I'm actually thinking about and that I'm talking about all have exactly the same amount of length to them. So we're going to think about this as kind of a velocity field. So good. So that's the first thing. Now, fluid flow can be different things. It can be what's called laminar and unlaminar, and steady versus unsteady. So steady typically has the same thing to do with laminar, but pretty much what that means, again, is like, here's my tube, and I have fluid flowing through it, but I have some sort of obstruction. So what happens at the obstruction? So for laminar and steady flow, what happens in this case then is that what? The fluid is going to go around the obstruction, and it's going to do something like this, right? So these are my streamlines. So my streamlines are going to go around, but these streamlines never actually cross each other. So what defines this to be steady and laminar is the fact that the streamlines don't actually cross each other, and it's steady because the velocity vectors change direction, but the magnitude of the velocity stays the same. So basically meaning that if I was looking at velocity vectors, so here I would have a velocity v. If I was looking at this portion, I would also have the same amount of velocity here. So the magnitude of velocity would be exactly the same at any one of these given locations. So this is what actually makes it steady. So laminar means that basically they'll move around an obstruction, they won't actually wrap around with each other. And it's steady in the fact that the velocity vector magnitude stays the same. So it has the same speed going through it around this obstruction at basically all times. Unsteady basically means that the velocity is changing, so it's speeding up and slowing down. And then unlaminar, or what you want to call turbulent, basically means that these lines are going to cross with each other. So in a turbulent system, so let's say here was my tube. In a turbulent system, what would happen then is I might have some streamlines, but then out here, these things are going to start curling around and go in different directions, meaning that these things are actually going to cross each other. So this would be a turbulent system. So turbulent, and this would be a laminar system. So this is laminar and steady, where this would be turbulent and unsteady. Now, we talked about turbulent systems before when we talked about drag. This is one of the reasons that we get basically drag. So again, the streamlines that are happening back here, they're all going to cross each other. So here at some points, all of these things are going to cross with each other, which means that I have different velocities all pointing in different directions at some particular point. But again, this isn't always necessarily bad. So again, if you thought about something like if you drove very close to a tractor trailer, in that case, you get a pocket here, and then you can actually be carried forward by that pocket of air. So you can actually use less gas in your car by doing something like that. But yeah, so it's not always bad, but typically it does lead to a lot of drag and other types of situations. So for us, we're going to make some approximations when we actually start talking about our dynamical fluids. So the first thing is we're going to ignore viscosity. Right, so again, this would here be a viscous fluid. This is non-viscous, meaning that we're going to ignore that kinetic friction basically towards the outside so that the velocity vectors will all have exactly the same amount of velocity. So this will be a constant vector field. So our first assumption is that we're going to, again, assume that this is true. So we have a non-viscous fluid. We're also going to assume that it is laminar and steady, okay? So that all of these things have exactly the same amount of velocity at all points, unless it goes into a section which has a smaller cross section. We'll talk about that next. What else? We're also going to assume that the density is constant all the time. Okay, so we're going to assume that the density of the fluid remains the same. We're also going to assume that it is incompressible. So we have an incompressible fluid. Again, we're going to assume that it is constant density, constant rho, that it is non-viscous, that it is steady and laminar. And the last assumption we're going to make is that this thing is what's called irrotational, which basically means that what? If I had a particle, say, flowing across here, it would be able to follow these field lines, but it would never actually rotate about its own axis, where that would not be true here. So basically, if I had a particle, let's say the fluid is flowing in this direction, it would actually come across here until eventually it ends up in like a whirlpool here, where it's just going to sit there and it's going to rotate about its own axis. So a rotational fluid is one where it would actually have, say, like a particle sitting inside of it, which is rotating about simply its own center of mass, so its own kind of rotational axis. So here we don't want that, so we want to assume that this is an irrotational fluid. So these are going to be our restrictions on the types of fluids that we can talk about. We're mostly doing this because that's the only way we can really talk about them mathematically. So if we had, say, viscous fluid, which was turbulent and unsteady, basically we don't have a way of actually being able to talk about those in a closed form way. So we have to then assume a whole bunch of different approximations and then basically do computer simulations to try to basically figure out what's actually happening. So there's no nice way of doing viscous and turbulent systems. If you want to do those, like I said, you basically have to do computer simulations with approximations and then look at each one basically independently. There is no general way of actually dealing with those. So this is what we're going to talk about for dynamical fluid. So when we think about the fluid, we want to think about, again, this non-viscous way of looking at the streamlines, where these streamlines are steady, basically, again, meaning that the density and the velocity inside of the tube will remain the same, unless it moves into another tube with a different type of cross-sectional area. So that's the next thing we want to look at. So what if I have a fluid moving from one tube into another tube where these two have two different cross-sectional areas? Now again, we're concentrating on a particular type of fluid, and again, this is going to be our incompressible fluid, so we know that the volume and the density has to remain the same. So good. So let's say we have something like this. So here I have one tube. That's then connected to another tube, which then has a, say, different cross-sectional area, where in this case I'm choosing that it has a smaller cross-sectional area. Okay. So if I was looking at a point here, point 1, this is then going to have a velocity vector pointing in this direction. So again, all the velocities here are exactly the same direction and exactly the same magnitude. And if I was looking at some point here, let's call this point 2, then the velocity vector here is going to be different because this has a different cross-sectional area. So here I have a cross-sectional area A1, here I have a cross-sectional area A2, and I want to know, okay, what happens to the velocity as I go from this tube to this tube? Does it increase? Does it decrease? Does it stay the same? Okay. So good. So talk about this. So again, what we know is all the points across here, all these velocity vectors, i.e. this vector field, has exactly the same amount of velocity. Now, if I look at a time frame of delta t, what's going to happen then is that all of this fluid here that started here is going to move to this location here, meaning that it's going to sweep out this amount of volume here. Okay? Where here, this is going to go forward an amount of L1, which is simply equal to V1 times that time frame of delta t. And again, this is going to sweep out some volume in here, where that volume V1 is then going to be equal to the cross-sectional area A1 times L1, which is then going to be equal to, what, A1 times V1 times delta T. So that's the amount of volume which is swept out here. Okay. Now, in the same amount of time, the amount of fluid that's here is going to sweep out some distance here of L2, which is going to be defined by this volume here. So in this case, what I know is that volume V2 then is going to be equal to A2 times L2, but again, L2 is simply going to be V2 times delta T. So in this case, this is going to be L2 times V2 times delta T. Okay, so this is the amount of volume which is swept out here. Now, again, here I'm assuming that these are incompressible fluids, which basically means that, again, the amount of volume here has to be exactly the same amount of volume here as long as these two time frames are exactly the same. So, as long as the delta t's are the same, that means that V1 then has to be equal to V2, which means that I have to have A1 times V1 times delta t must be equal to A2 times V2 times delta t. But those delta t's are the same, so they have to cancel. So this tells me that A1 times V1 then must be equal to A2 times V2. So all this means then is what? If I go from one cross-sectional area to another cross-sectional area, then this product of the area times the velocity must be the same at any point along this tube. Okay? So ultimately, what this means then is that the area times the velocity must be equal to a constant. This is what's known as the continuity equation. So the continuity equation simply says that the cross-sectional area times the velocity of the fluid, the incompressible fluid, within inside of this tube must be constant at any location. So again, whether I decrease in cross-sectional area or I increase in cross-sectional area, this thing must be constant. Now, this also says is what? If I go from a large cross-sectional area to a small cross-sectional area, what has to happen then is that the velocity of the fluid has to increase. Right? So here, if I go from a large cross-sectional area times the velocity to a small cross-sectional area, well, this velocity has to increase to make sure that this proportionality stays the same. So whenever we go from a large cross-sectional area to a small cross-sectional area, the velocity must increase. Right? Do we know that already? Yes, right? We already know that because when we go in our yard and we have a hose and we turn on the hose and we want to spray our friend or our mom or, you know, something like that, what do we have to do? Well, if we point the hose directly at them, right? The hose has a large cross-sectional area, maybe about this size. The water kind of like trickles out, right? Kind of goes, that's about it, right? So what do? Well, we put our thumb partially over then that hole. So again, if this was my hole size, I put my thumb partially over it. So what I'm doing in that case is I'm restricting the cross-sectional area, which means the velocity has to increase. And in that case, the velocity of the water increases and it can shoot actually much further. So if I want to shoot a farther distance, I simply have to restrict the cross-sectional area, make it smaller, to increase the velocity at which the water is coming out, to then have it shoot further. So this is the continuity equation. So, good. Now, if I did the opposite, if I move from a small cross-sectional area to a large cross-sectional area, so in this case I go from small to large, well in that case if this increases, this has to decrease to make sure this proportionality stays the same, which means that the fluid would have to decrease, right, in velocity. So good, so this is what we call the continuity equation. So next thing we're going to look at is, well, what happens if I not only change in cross-sectional area, what then happens if I change in height as well? So let's say I now have a situation like this. So here is now my tube, my original tube. So it's coming in like this, but then this thing is going to increase in height and then go to, say, this final location. So this thing is going to go up and then do something like this, right? Where this side has a cross-sectional area A1, this side has a cross-sectional area A2. And let's say initially this is at some height relative to some 0 location. So let's say this is our y is equal to 0 location. So this is at a height of y1, at least the center portion of the tube. And then this portion here, relative to that same location, is then at another height of y2. Okay. So again, here what's happening is I have fluid which is changing cross-sectional size. So it goes from one size to another size, and then it also changes height. And again, we want to look at an incompressible fluid, so that again, the mass and the volume must remain the same as this thing is actually moving through. So good. So good. Let's do basically the same idea. So again, let's choose a point here, call that point 1. So again, we know the velocity moving in this direction has a velocity v1. And then by the time it gets over here, this is going to be, say, point 2. And here it's going to have a new velocity, let's call that v2. Now, the way we're going to do this is, so here I'm going to have a change in velocity, but I also have a change in height. And we now know that whenever we deal with changes in velocities and changes in heights, we have to consider conservation of energy. Right? That's the easiest way to actually do these problems. So here we're going to look at the change in kinetic energy plus the change in potential energy. And all that's going to be equal to the work done by the non-conservative force. So let's deal with that in just a second. So let's say it starts here and it finishes there. So my change in kinetic energy is going to be 1/2 the mass times the velocity v2 squared, because that's my final, minus my initial, which is 1/2 m v1 squared, plus my change of potential energy, which is then going to be what, m times g times y2 minus m times g times y1, must all be equal to the work done by the non-conservative force. So in this case, do I have a work done by a non-conservative force? Well, the answer is, let's think about it. So if I had water just sitting inside of this tube, does the water want to go in this direction and move up? Well, no, right? Nothing actually wants to move upward. It wants to move downward. So in this case, if the water was just sitting here, it would want to move in this direction. It wouldn't want to move in this direction. So to get it to move in this direction, I have to push on it, right? I'm going to have to do work. So in this case, the answer is, well, yes, because I'm going to have to push it in this direction, right? So here, I'm going to have to apply a force in this direction, let's call that F1, to move the fluid this amount of distance, let's call that L1. Right? So basically, again, what's going to happen is this is going to sweep out a volume here to move this guy in this direction. But what's happening is here, since I'm pushing the fluid here, this fluid wants to move forward, but in front of that there's a fluid sitting here, which means that I'm trying to push this fluid through a fluid which is already existing on this side. Now, does the fluid here want to easily be able to move through this fluid which is already sitting on this side? Well, again, the answer is no, right? So this would be me trying to push myself through this wall. This material that's sitting here doesn't want to get moved, so what I have to do is I'm going to have to, what? Push into this direction, but simultaneously this stuff is pushing me back in this direction, which means that the material that's sitting here, the fluid that's actually there, is going to push back onto the fluid up here, applying a force in this direction. Let's call that F2. Now, but ultimately, this one is pushing this direction, which means that this fluid that's here is still going to sweep out a distance L2 here, which means that this is going to sweep out, again, a volume here. So this is going to be a volume V2, where this was a volume V1, right? So ultimately what's going to happen then is I'm going to have two works, right? I'm going to have two non-conservative works. I have this work, which is adding energy to the system, trying to get it to move. So this is going to be an additive work done by non-conservative force. Simultaneously, what's happening here is that this fluid is pushing back in this direction, which means that this is going to be a dissipative work, which means that it's taking work or energy out of the system. So my total work done by the non-conservative force then is going to be the work done by 1 plus the work done then by 2. Now, in this case, since I'm applying the force in exactly the same direction as the velocity, or as in exactly the same direction as the displacement, here I'm going to end up with F1 times, let's see, so F1 times L1, right, times then cosine of 0 degrees, since they're in the same direction, which is just simply equal to 1. So for this one, I'm going to end up with an F2 times L2, but in this case, F2 is pushing this way, L2 is pointing this way, so I end up with a cosine of 180 degrees, but a cosine of 180 degrees is simply equal to -1. Now in this case, it's much easier to talk about the pressure. So this force results in a pressure P1, where this force results in a pressure P2. And we know that force is the same thing as pressure times area, because pressure is force per unit area. So I'm going to rewrite this then as what? The pressure P1 times cross-sectional area A1 times L1 minus then pressure P2. It's like a row. There we go, P2 times A2 times L2. But since again, A1 times L1 is simply this volume, A2 times L2 is simply this volume, but since this is an incompressible fluid, I know this volume has to be the same as this volume, which means that this is the same volume as this one, so we can then factor it out. So it's going to be the same thing then as P2 minus P1 all times the volume. So putting that in here, this now becomes 1/2 the mass times V2 squared minus 1/2 the mass times V1 squared plus the mass times GY2 minus M GY1 is then equal to the pressure P2 minus the pressure P1 all times the volume. But here, I could rewrite then the mass, all of these masses then as simply the density times the volumes. Since this volume is the same as this volume, same as this volume, same as this one, same as this one, all those volumes are simply going to cancel out. So at the end of the day, this is going to become 1/2 the density V2 squared minus 1/2 the density times V1 squared plus the density times GY2 minus the density times GY1 is all equal to the pressure P2 minus the pressure P1. Now, finally, I have 2's and 1's, but I can leave all the 2's on one side and bring all the 1's onto the other side. Oh, sorry. I switched that here. This should be P1 minus P2. Sorry about that. You guys are supposed to point these things out to me. P1 minus P2. P1 minus P2. There we go. Good. So all I'm going to do is I'm going to bring all the 1's on one side, all the 2's on the other side. So ultimately what this thing is going to tell me then is that 1/2 the density times V1 squared plus the pressure P1 plus the density times GY1 must be equal to the pressure 2 plus 1/2 rho times V2 squared plus rho times G times Y1. So all this says then is that what? That the pressure plus 1/2 the density times the velocity squared plus the density times G times the height must be equal to that of the same exact thing at a different point. So ultimately all that says then is that the pressure plus 1/2 times the velocity squared times the density plus the density times G times Y must be constant at any point along this particular tube. So finally what we get then is 1/2 rho times V squared plus G times rho times Y plus the pressure must be equal to a constant at any point along the tube. Okay. This is what's known as Bernoulli's equation. So Bernoulli's equation simply says that this thing must be constant at any particular point. Now, let's talk about the pressure. So first of all, the pressure here is not the pressure that subobstruction would feel here, but it's actually the pressure that's being felt by the walls in this case. So as the fluid is moving, that's the pressure that it feels on the walls. Now, what does this also say? So this also says that what? At a given height, y, if the pressure increases, then the velocity has to increase. I'm sorry. If the pressure increases, the velocity decreases, but if the pressure decreases, the velocity then must increase. Now, what does that mean? Well, that means that, let's say I have a piece of paper here. It's going to work. And I'm going to turn this into an airplane. So why does an airplane actually fly? Let me fold this guy. Make sure this is beautiful. Well, this flies because what happens is that what? If you think about a wing, what's happening is above the wing and below the wing, there is air flowing over top of each one of those two. But what happens is what? To make sure that the thing is either taking off or moving upward or moving downward, or at least being stationary, right? So if I think about my wing, so here's the wing of an airplane, right, doing something like this. So what I know is that this has a mass, so it means it has a weight downward. Here there's a pressure downward, so this is my pressure down. Here there's a pressure upward. So basically, to make sure that this thing doesn't fall, there are two forces downward, there's one force upward from this particular pressure, so the pressure down here must be greater than the pressure up here. Well, what does that mean? So according to Bernoulli's equation, what that means then is that the pressure at the top, which is then less, then has a greater velocity. So as the plane is flying through the air, the particles which are then moving over the wing here are moving at a much faster rate than what they're moving below the wing. This then causes the lift into the airplane, which causes this guy to actually move upward. Now, if this was a sail, like a sailboat, in that case it would have the sail upward. So what happens in that case then is the wind is coming in, the wind has a higher velocity over here than it does on this side, which means it has a force. But the rudder on the bottom is also moving in the water, where part of the water on one side of the rudder versus on the other side is moving faster, which then causes this thing to ultimately be able to sail. So the reason that this thing can fly through the air is because the air moving below the wing is moving slower across the wing than it is moving above the wing, which then causes this thing to actually be able to stay stationary or move up or move down. Other things that this is used for are things like, so if you think about cholesterol, having more pressure, right, on your veins, right, your arteries, as opposed to less cholesterol. So if you have less pressure, that tells you how fast your blood has been moving, right? So if you have high blood pressure versus low blood pressure. So if you have low blood pressure, that means that what? The velocity is moving faster, versus if you have high blood pressure, that means that the velocity is moving slower in those particular cases. So Bernoulli's equation basically governs anything that is moving. So One thing to point out, though, is Bernoulli's equation almost never goes by itself without the continuity equation. So basically what's going to happen here is a lot of times you won't know the velocity here, or you might know it here, but you don't know it here, for example. So, but what you do know is the cross-sectional area here, and you do know the cross-sectional area here. So what you'll have to do is use the continuity equation to figure out the velocity at this point due to the fact that you know how these cross-sectional areas relate to each other. And then from there, you'll use Bernoulli's equation the rest of the way to solve for whatever it is that you want. So again, Bernoulli's equation is simply conservation of energy. That's all we did. So all it's saying is as this fluid is moving through, energy has to be conserved. But in this case, the energy is conserved in a way that we are actually doing both positive work and negative work onto the system, or at least the fluid is. So the fluid that's pushing this way is doing positive work. Fluid that's trying to push back in this direction is then doing negative work. But ultimately we have to do work onto the system, but the energy has to be conserved. So that's all this thing is saying. But yeah, Bernoulli's equation just says that the pressure plus 1/2 the density times the velocity squared, that's basic kinetic energy, plus the density times g times y, so this is the potential energy, must be a constant at any point along this particular tube.